Electric field. The electric field is a region around a charged particle or an object that exerts a force on other charged particles or objects. To find the electric field due to one charge, let's begin with the magnitude of the electric force between two charged objects. And that, of course, is Coulomb's law. The only difference we're going to do here is assume one charge is very, very large, that's Q, big Q, and the other is a small, and we call it a small positive test charge. And we're taking the magnitude of that to find the magnitude of the electric force between the two charges, big Q and little q. We'll start here with Coulomb's law, and we will find the electric field, and we're going to give that the symbol E. We'll find its magnitude due to the larger charge, and we're going to divide the force by the smaller charge, little q. So the electric field is going to be the force divided by a small charge there. So that will be K big Q over R squared absolute value. Like the electric force, the electric field is a vector. Here we're just showing the magnitude of it. And we're going to define the vector direction as away from a positive charge Q and towards a negative charge negative Q. The units for the electric field are newtons per coulomb, or, abbreviated here, N/C. More on the direction of the electric field. It's determined by the direction that a positive test charge, see we brought the charge back now, we divided it out, now here it is again, and the direction that that will move or accelerate if placed in the space surrounding a charge plus Q. So, what would happen if an isolated positive test charge were placed near a positive charge big Q? Well, we've kind of given it away there. It will have an acceleration away from the large charge Q because like charges repel. And he's not moving because we're assuming this is very, very large compared to the little charge. This reiterates what we said on the previous slide. The positive test charge, which is this little q here, would accelerate to the left, away from large Q. Like charges repel. The isolated positive charge plus Q, this big guy over here, will repel a positive test charge. Therefore, the direction of the electric field surrounding the positive charge points radially outward or away from the positive charge in all directions. And this is actually a three-dimensional field, so it would also be coming out of the page and into the page. What if we have an isolated negative charge, negative Q here? That will also create an electric field, but in this case, a positive test charge will move towards negative big Q. So, the electric field lines point inward towards the charge. Why? Because opposite charges attract. We can also see something else from this little pictorial here. The strength of the electric field decreases as distance increases. We saw that from the formula, where the electric field is proportional to the force and proportional 1 over r squared. We represent that on the page here by the density of the field lines. The electric field lines are closer together in this area when they are closer to the charge that is generating the field. This indicates the electric field is greater near the charge. And another word about, let's say we have the little positive test charge here. We said it was repelled and will move in that direction. We're assuming this charge is immobile. Okay? It's either fixed to a surface or it is just so massive in mass that any acceleration it feels is tiny compared to this guy. So we're assuming this is stationary and the test charge is the one moving. Now, of course, it generates the field whether it's moving or not, but we just wanted to be clear about the definition here.